the very end. I forgot to mention in my last lecture, this is a really old but really still fantastic book, Introduction to Statistical Pattern Recognition by Fukunaga. Has most of what we have covered thus far and what we will cover probably today and maybe for another class or so. There are other books that I posted in the syllabus and also in the introductory video that is available in YouTube. So you guys know there are all the video lectures, all the lectures that we're recording here available on YouTube. So you can go back to that if you have questions. And if not, just email me or the TA for any other additional details that we're missing or you're missing. All right, so let's go back to what we were discussing last week or last class rather. We're talking about how to understand our feature space. So remember that we were considering the example of images. So if we have images of faces, for example, or whatever other object that you're representing, each face is represented by a certain number of pixels, right? And we call this xi. So for example, this could go from x1 through xn. So x, it's our vector, x2, xn, and the number of elements or samples that we have. And then each xi is a vector that's represented by a number of pixels. Let's say p the number of pixels, xi1 through xip. That's what we had. And what we said is if we're going to represent this in a space like Rp, the real domain of p dimensions, then each dimension represents one of these xij's and xiks, right? So that the entries of xij, xik identify where in that space I'm at, right? In that feature space. So that's my feature space. And now what I want to understand is what are these dimensions, right? And one thing that we discuss is that in the real domain, we assume that these dimensions are orthogonal to one another, right? Because basis vectors, let's call this one I hat, or actually, let me call them, I don't want to use the same I. Let me call it EI or EJ, and this basis vector here, EK, okay? So these basis vectors are, of course, orthogonal with one another. That's what defines a real domain, right? But my samples may actually be correlated, meaning that these two dimensions are correlated given these samples, right? So for example, in that case, there is a linear function f, right? Such that given my value xij, I know exactly the value of xik, right? There's a linear function, right? F here has to be linear. That gives me a perfect mapping between one feature and the other feature, the j feature and the kth feature, or the j dimension and the kth dimension, okay? Right? Now we call this being correlated, as we discussed. In that case here, there is some correlation, right? So given my value xij, I can find a linear function that gives me an idea of what xik is, but not a perfect idea. Most likely this is going to be let's say xik equal to f of xij plus some noise function, right? Let's call it n. And then in this case here, there's actually no correlation, right? So we're going from 100% correlated to not correlated, and in between, there might be some correlation, right? Okay, and we were discussing how we're going to find out what how correlated the data are. And to do that, well, we were using the equation of a line. So we agreed that to describe this line here, I can write the simple equation of a line. And the equation of a line obviously we use A's, I believe, A1 xi1 plus all the way to AP, did I say? Yeah, P xip, right? Minus D equals 0, right? So that's the equation of a line. And obviously, that is my linear function f, right? And then I add these over all the possible i's from 1 through n. OK? So far, so good? OK, so this is what we had. This is where we were. We also said that this is never going to be equal to 0 unless they are correlated. And therefore, what we can compute is the square of this and call this the error function. So this is equal to r, right? And if we solve for this, this is called, as you may know if you've taken image processing with me, linear least squares. Right? It's called linear least squares because we compute the square and we want to now minimize this, right? We want to find the least possible value for r, right? So that's what we did. So we had this equation here. We assume for the time being that d is equal to 0, in which case we end up with a set of homogeneous equations, right? So let me write them for you. The first equation would be A1 x11 for the same sample, the first sample, excuse me, AP x1p equals 0. And we have n samples, so we go to x n, is it n? Yeah, n1 plus AP x np equals 0, right? This is our system of equations. Now, of course, if n is equal to p, and all these equations are linearly independent, then there is a unique solution, right? But if n is larger than p, and the equations are linearly independent, then there is no solution, right? That's when we use the technique that we learned in image processing, linear least squares, to derive this. So we can write this as a product of matrices. So we're going to have x1 transpose, right? This is x11 through x1p vector, this vector right here, right? All right. This as a row of my matrix X and all the way to xn. So here they're going to be rows. And I'm going to define my vector A, which has, so this is a vector, A1 through AP. And with that, I can now rewrite my equation as XA equals 0. So I have now this equation right here, XA equals 0, right? A vector. Now, I want to compute the square of this and then find the least possible error. So the square of XA is A transpose X transpose XA. And we call this Q, I believe, right? Yep. And therefore, we have our equation A transpose QA equals lambda. Lambda is my error that I have here, right? The error function R squared. This is the error I have. And what does this mean? That means that when I solve this system of equations, depending on the A vector I select, right, I'm going to end up with more or less error, right? And what do I want? I want to minimize my error in least squares, right? Which means I need to find the A vector that minimizes that equation, right? And that equation is the same thing as this system of equations, right? Right? That's where we were. And then we said that we can call this the P vector. This is my A vector P that gives me the smallest possible lambda. And then I can have also P minus 1, which gives me the second possible smallest, constrained with the additional constraint that AP minus 1 be equal to 0, because they have to be orthogonal to one another. Okay, remember that? And so on, right, for all the possible dimensions or A vectors that I can find solutions for, right? Now, what that means in reality, because this is a symmetric, right? This X transpose X is a symmetric matrix by definition, because X transpose X has to be symmetric. There's no other way around it. And it has to be positive. It can be semi-definite, right? It's either positive definite or positive semi-definite. Positive definite means, you may recall, that all the entries and therefore all the eigenvectors that we can extract from that matrix are positive, right? Or all the eigenvalues, excuse me. Semi-definite means that some of these eigenvalues might be 0, right? Okay? Now, if some of the eigenvalues are 0, meaning that this matrix is semi-definite, then there is a solution for this system of equations, right? Right? For which I can actually obtain a 0 error, right? Which is fantastic. All right, great. So I'm going to write this equation up here as A transpose QA equal capital lambda, where capital A are the entries A1 through AP, and these are the AP vectors, right? So these are these vectors here that I have. And lambda, it's a diagonal matrix of corresponding eigenvalues, lambda 1 through lambda p, right? And we also said that because of the way we structured this, lambda p is the smallest of our eigenvalues. So lambda p is the smallest one, which is either larger or equal to 0. It could be 0, but it cannot be smaller than 0. And this is, of course, smaller or equal than lambda p minus 1 all the way to lambda 1, right? OK, this is a quick review of what we did in our last lecture. That's where we were at. Now, this equation here, where is it? This equation here is a famous equation. You've probably seen it before. It's called the Schur decomposition or Schur equation. And if we move it around, right, because obviously as before, A, capital A, this capital matrix here, is a matrix of orthonormal vectors, right? Because we said that this is an eigenvalue decomposition equation. So these are the eigenvectors. And these are the corresponding eigenvalues. Right? So A transpose A is equal to the identity matrix. So I can multiply this here and rewrite this as QA, and now move A to the other side as A gamma, or excuse me, lambda. And this, obviously, is the famous eigenvalue decomposition equation, right? Right? Now, A in this last equation is a matrix whose columns are the eigenvectors of capital Q, and lambda, it's a diagonal matrix whose entries are the corresponding eigenvalues, right? So the first eigenvector, call it A1, corresponds to the eigenvalue lambda 1. And so on, right? Now, lambda 1, it's our largest eigenvalue, right? All right, so let's go back to this. Remember what we said last time? This equation is nothing else than projecting the information of our matrix Q onto the space defined by the basis vector A, right? Remember that since this is an eigenvalue decomposition equation, we have made the assumption, other than these ones that I've stated here, that these vectors have length or norm 1, right? The true norm of these vectors is 1. This is a constraint. And we did that. Remember why? Because, what is it? These equations are defined up to scale, right? So you have to select a scalar. Now, there's obviously a trivial solution to this. All a is equal to 0. Yeah, that's called the trivial solution, right? We don't care about the trivial solution. We want something that is non-trivial, but for that we need to specify a scale, because multiplying this side by any scalar s and this side by any scalar s gives us the exact same result, right? So we have to set up a scale for our vectors A, because they could be multiplied by any s different than 0, and you still have a solution, right? Okay, or larger than 0. So this equation right here means that I'm projecting the information that I have in that symmetric positive semi-definite matrix onto that dimension specified by A, right? So A here specifies that basis vector here, A1, okay? A1 vector is a basis vector that specifies a dimension in my original feature space, right? And what does lambda represent? Lambda represents the span or variance, right, of the data that I have once the data is being projected onto that dimension, right? So that's defining lambda, right? Here, A1 would be this one, which defines this dimension here, right? Okay. Lambda 1 would specify this span right here. Now, what would be A2? A2 would be, anyone? Orthogonal to that, very good. So it has to be this one. In 2D, there can only be another one, right? It has to be this one, and that is this dimension. So if I now project all this data, so this data had to be projected here, right? I forgot to do that, my bad. And now in this dimension, I projected it onto A2, and I get this projection. And therefore, this specifies lambda 2, the variance of the data in that dimension, right? Right? Any questions? All right, this was the review of what we saw last time, so I hope this is clear, right? If not, that's a time to ask, because we're going to be using this constantly in this class. Yep, question.
Is there any explanation of why lambda is the variance of the data?
It's proportional to the variance, right? It's because of the error, right? Remember, what are we trying to do? Lambda is nothing else than the error of trying to fit a function, right? So when I have this projection, right, so these points, and please, if you haven't taken the image processing course, take it. And if not, at least watch the videos online, because I explain this in tremendous detail over weeks rather than seconds. So here, when you project these vectors onto that dimension, right, you are projecting them orthographically onto that dimension, right, meaning 90-degree angles here, right? Now, this distance from where the vector is going to be represented at this point to that point, that distance right here is the error that you're accumulating here. That's what this lambda represents, okay? Represents the error of the span of what you're representing. Other questions? No? Sure? Okay. So the question then becomes, how do you represent this, or how do you compute rather this? And there are many techniques to do that, but primarily there is a technique that you know about and that is very useful in all of machine learning that's called Lagrange multipliers, right? So I'm not going to cover Lagrange multipliers here, but let's give a very quick overview of what that would entail. So just as a very quick overview of Lagrange multipliers, let's think about, let's do this. Let's think about the 2D plane. So imagine that you live in the 2D plane, right? And you have a function, I'm going to call it, say, g, right? And for any point p for which this g is equal to 0, p a point in my two-dimensional plane, right? For any point p for which this function g of p is equal to 0, it means that that p is on that curve, on that curve right here represented by a function, right? Yep. Okay. Now, imagine I have 2 points on that plane, P1 and P2. Okay? So far, so good? Now, my task, my goal, is to go from P1 to G, to any point on G, right? Gp equal to 0, right? And then from that point to P2. And I want to find the shortest path to do that on the 2D plane, okay? All right, so how am I going to do that? Well, if I want to find the shortest Euclidean path, right, then the first thing that I need to do is to find how far away I have walked, right? Now, if I have to go from that point to any other point on the plane that are at equal distance, that defines what? Circle, S1, right? So the circle, S1, defines all the points that are at an equal distance from here, right? Now, if I keep growing this up to the point where it's tangent in a point with G, that is the shortest path I can walk to GP, right? Or to the G function, right? Obviously. Any other point is going to be farther away. I need to walk longer, right? And how do I know this? Well, notice that at this point, P here, the norm of this function and the norm of the point on the circle are exactly the same up to a scale, right? How do I represent them? I can represent them with the gradient, right? The gradient of both functions are equal up to a scale. Okay? I could do the same thing here for this point 2, right? I could keep growing this until at some point it's tangent, right? And find the closest point to P2 that's on G. Okay? But that's not what I want. What I want to find the point that is common, that is closest to P1 and P2, right? So if I combine these two circles into one, what do I get? Two circles, an ellipse. Very good. So if I were to combine these two, I'll get this ellipse. And I do the same thing. I keep growing the ellipse until it's tangent, right, to some point P here. And what does this mean? It means that this gradient and that gradient are exactly the same, right? That's what this means. So I have, I'm going to write this as, let's see, this is the gradient of my function, right? The function that of the ellipse, and this is the gradient of G. Okay. So f, let's define this. F, my function, is the distance, the Euclidean distance, let's call it d, from P1 to my point here, P, right? Plus the distance from P to P2, right? And G, we have it right here. And now I know that the gradient of F has to be equal to lambda, the gradient of G. Yes? All agree? All right, excellent. Now that's the same as saying that the gradient of F minus lambda, the gradient of G, is equal to 0, right? I haven't done anything spectacular here. That gives me P plus 1 equations, right? P equations for the P dimensions that I have in my space plus this extra equation that I have, right? So I have P plus 1 equations, and I have, of course, P plus 1 unknowns. So therefore, this is a system of equations that has a unique solution, right? All right. Now, let us see how this would work to find the eigenvectors of Q. We want to maximize, remember, A1 transpose Q A1, right? We want to maximize this because that's the largest eigenvalue, right? So we're going to write A1 Q A1 minus 1 equals 0, right? A1 transpose A1 is equal to 1, right? Because these are orthonormal vectors, right? So the length of that vector, A1 transpose A1, it's the 2 norm of the vector. It's equal to 1. I'm just writing it as A1 transpose Q A1 minus 1 equals 0. Same thing. And now I'm going to differentiate the two functions that I have, F and Q, right? Or the ones that I have here, corresponding ones, with respect to A1, right? So if I differentiate this, I'm going to get, let's see, here I'm going to get, right here it's QA1, right? Correct? And then the other one, with it here, this one here is going to be lambda, right, times my vector A1. This has to be equal to 0. And if I move these things around, I'm going to get QA1, it's equal to lambda A1. And does this look familiar? It's the same thing, isn't it? So the eigenvalue here in eigenvectors can be computed using Lagrange multipliers. In fact, the eigenvalue is nothing else than the Lagrange multiplier, right? Now you can use this type of tricks and techniques to solve a number of problems in machine learning, and we will probably do that in the future. Okay? All right? Questions? All right, so let's move on. Another thing that it's worth mentioning, since we're talking about this, it's something that's called the universality principle. That says that given a symmetric positive definite matrix Q, right, as the one that we have defined here, what is it? Right? This matrix Q that we have defined here before. Okay? Is there a question? No? Okay. But with the peculiarity that all the entries in X are randomly generated. Okay. Now, if the entries of X are randomly generated, so are the entries of Q, only that it's a symmetric positive semi-definite matrix, right? Right? This is called a random matrix. Okay? This is called a random matrix. Now, if you do an eigenvalue decomposition of Q, as we have shown here, right? You extract the eigenvectors and eigenvalues of Q. You sort the eigenvectors as we have done, right? So we have lambda 1 is larger or equal than lambda 2, all the way to P, which must be larger or equal than 0 because Q is positive semi-definite. And now you plot the distribution of the difference of consecutive eigenvalues. So you do lambda 1 minus lambda 2, and then lambda 2 minus lambda 3, and so on. And you plot the distribution of these distances, right? So in this dimension, you have the distance between lambda I plus 1 and lambda I, right? And now you plot this distribution. So here's the frequency, right? How frequent that is. That distribution looks something like this. So a way to know whether my matrix Q is actually random, it's a random matrix that doesn't represent anything but randomness, it's actually to look at that distribution. Okay, so by just looking at the distribution of my matrix, I already know whether it's potentially random or not. Isn't that cool? That's all I need to know. But it's even more interesting than this. Now, if you take the distribution of the zeros of the z function, it's a function used in mathematics that specifies when you take all the zeros of that z function, you get a distribution of the prime numbers. It's really odd, right? Well, if you take the distribution of those zeros, and the eigenvalues of that distribution, it has the exact same type of form that I have shown here. Okay? What else? It was reported recently, actually, that the distribution of the cones, if you haven't taken image processing, are sensitive to specific colors and are located at the back of your retina, right, or in your retina, the back of your eye, right? But if you take the distribution, that means the spatial distribution, the location of the cones, to a specific or to distinct colors, rather, in the retina of the chicken, you also find that distribution right there, as if they were randomly distributed. This fact is known as the universality principle, precisely because you find it all over mathematics. No one has any idea why this is the case. This is a huge problem in mathematics right now. This is pure mathematics. It's just trying to understand why that happens. What are the conditions? What are the properties of this huge, very important problem? But for us, what this really tells us is that there are ways to know the structure of the data represented in our Q matrix. So that matrix Q, which remember, it's nothing else than my samples, right, multiplied by my samples, right? So that's it, square of the samples. That distribution actually tells me, or has a lot of information, that matrix has a lot of information about the distribution of my data. Okay? And we're going to try to explore this. The universality principle is one of them. The other way to extract information that hopefully we'll get to it today, it's called principal components analysis. So let's see if we can get there. Okay. So let's see. Let's see what else we can do with these wonderful matrices. Okay, remember that I assumed that D was equal to 0, right? I assumed that. Unfortunately, D is not 0, right? So generally, in the general case, D is different than 0. So what are we going to do? Well, if I have my equation, r squared, the error squared, it's equal to, from 1 through n, of a1 xi1 plus a pxip squared, excuse me, minus d squared, right? And d is not equal to 0, I somehow have to factor this out. And how am I going to factor this out? Well, remember, I want to minimize, right, or maximize this equation. How do I find this? By computing the derivative of this equation, equaling this to 0. This is a point of a maximum or a minimum, right? So this is exactly what I'm going to do. I'm going to compute the partial derivative with respect to d, which is the variable I still have to solve for. And this is equal to, let's see, this is equal to, remember, I'm computing the derivative with respect to d. So this is an element square, so this is going to be 2 times the sum. The derivative with respect to d is, of the inside, -1. Good, so I'm going to put it right here, negative, times this again, right? This element, this big element, okay. Oops. And again, 1 through n. Yep. And we're going to equal all this to 0. And now I want to represent this in a compact form. So what I'm going to do, let's see, I'm going to say that d, let me take this d out, right? D is equal to a1 mu1 hat, and what else? Plus all the way up to ap mu p hat, right? Where mu I hat is nothing else than the sample mean of my xij's, right? So n minus 1 of the sum from 1 through n of xij. Right? The sample mean. And again, all I did is I move d to the other side, and I get this equation, right? Let's write this equation maybe for a second. Let me write this for 2D, 2 dimensions. It'll be easier to work with. So I have d equal a1 mu hat 1 plus a2 mu hat 2, right? Okay, let's work with 2 dimensions. It's going to be likely easier. So with that, I can rewrite R2 that I have here, right? This equation as the sum from 1 through n of A1 xi1 minus mu1 hat plus A2 xi2 minus mu2 hat. Correct? Right? So all I'm doing is I'm rewriting this, right? So that now instead of D, I substitute D for this, right? And end up with this, right? Simple enough. Okay. I can rewrite this in matrix form as we did in our last lecture and as I reviewed today. So I can write the matrix U, which is going to be x11 minus mu1 hat and x12 minus mu2 hat, right? And all the way to xn1 minus mu1 hat, xn2 minus mu2 hat, right? This is the same I did before with x, but now I call it u because it has the x's minus the mean, right? The simple mean. And now, as we did before, remember, we want to compute the square of this because this is r squared, right? So r squared is nothing else than ua squared, which, as before, is A transpose U transpose UA. Now let me call this U transpose U, I'm going to call it sigma x. And what is sigma x equal to? Let's see. Sigma x is nothing else than U transpose. So we transpose this. So now I have this as columns, right? Times this. OK? So I'm going to have this first as column. So I'm going to have now this as a row multiplied by this, by its same row. So I'm going to end up with, let's see. The first one is going to be x1, actually, let's do xi1. Let me do that. xi1 minus mu1 hat square, right? So I'm going to do this one times this one. So I'm going to have all the xi's multiply with themselves. So we squared, right? Sum over 1 through n. Yes? Yeah? OK. And the same is going to happen here in the other diagonal element. But now I'm going to have xi2 minus mu2 hat square, right? And what's going to happen in the off diagonals? I'm going to have this one, right? This first column, which is going to be a row now, multiply by the other columns, right? So I'm going to have, if I have a two-dimensional case only, I'm going to have the sum of xi1 minus mu1 hat times xi2 minus mu2 hat, right? And this is going to be the exact same thing because that's obviously a symmetric matrix. Let's rewrite this in a more compact form. Sigma x, it's equal to the sum from 1 through n of xi minus mu hat times xi minus mu hat transpose, where mu hat is equal to mu hat 1 mu hat 2, right? Okay. That's the exact same equation as this, but in a more compact form, right? In fact, from here, it's trivial to extend this to p dimensions, right? You just keep going up to mu p dimensions. And obviously, xi is also equal to xi1 through xip of p dimensions, right, in our p-dimensional feature space. All right. This matrix right here, famous matrix called the covariance matrix. The covariance matrix computes, as you can see here, the second moments of the data, right? The mean computes the first moments. This computes the second moments of the data, right? Technically, I guess we should say again, as we said in the first lecture, they are the second central moments because mu hat, it's a simple mean, right? Fair enough, but people usually just call them the second moments, right? With that understanding. Now, what is sigma x? It's the exact same thing that we had computed before, but we first subtract the mean from each sample. What does this so-called mean normalization do? Remember that we had a representation like this, where we had samples here. Now, if I compute the sample mean, right, the sample mean here, and I subtract it from all these points, this is the same as shifting the axes of my space here, right? Because I am subtracting that vector, right? That's it. It's just a shift, a translation. I do that because now when I find the eigenvectors that I was looking for, the eigenvectors are defined with respect to the origin of my coordinate system, right? So if I had a problem like I had before, where my points are over here, right, and my eigenvector is here, this doesn't make much sense, right? I have to actually shift my coordinate system to a place where I can actually make sense of what I am computing. So the covariance matrix does exactly the same thing as the matrix Q that we had computed in our last lecture, but it does this once you have mean normalized your data. All right? Okay, now let's go back to this part of the equation here, right? Anyone can tell me what these two elements are called? We said it. What's that?
Scale variance.
The variance, yes, very good. Scale variance. This is the variance. You're right, very good. The scale version. Usually, you will normalize a covariance matrix as well, right? There's all these things are defined up to a scale here, okay? And there is, like with the mean, a biased covariance matrix and an unbiased covariance matrix, right? So these are the variances, right? So I'm going to call these say sigma I square, right? This one and this one. For the variance, that's the same equation that we saw first day of class. And what do we have in the diagonal? We have the covariances, right? The covariance between two dimensions, between two features. So the variance is the variance in a single dimension, right? Single feature. These other ones, which is the product, is the covariance between two different features, right? And that's what this is called the covariance matrix, because these two here are the covariances. Okay? So I called the variances sigma I square. So these ones I'm going to call sigma I times sigma j, okay, for the two dimensions I and j. Now, obviously, this is not exactly equal to sigma I, sigma j, but instead, this is multiplied by a scalar here, rho ij, okay? So the covariances are the variance about I, the variance about j, times a scalar. Anyone knows what this scalar is called? Very good, correlation. That's in fact what the correlation is. Remember that we started, I already erased that, but we started trying to find what were the correlations between these different features given the samples. These are the correlations, right? That's exactly what they are. They tell you the relationship between these variances across these different features. In fact, we can even write this in matrix form. Let's do that. Let's write this in matrix form, this final result. So I'm going to write this final result in matrix form as sigma x equal gamma, capital gamma, that's a matrix gamma, a matrix, let's call it R, and gamma again, okay? Where capital gamma, it's a matrix, a diagonal matrix, with diagonal entries sigma 1 through sigma p, the variance, and zeros in the off diagonal. And R is a matrix that has ones in the diagonal, and in the off diagonal, it has the correlation. So that would be the correlation of one, the first dimension with the second dimension, the first with the third, and so on, up to the first with the p, right? And here the same thing. That would be rho of 1p. It should be p1, but p1 and 1p are the same. So I'm just going to call them like this, okay? And anyone ventures to guess what this is called, this R is called? Remember, these are called correlations, so it's not a tricky question. The correlation matrix. Very good. Now, the correlation matrix must not be confused with the so-called autocorrelation matrix, okay? There's another matrix which is called the autocorrelation. Which is defined as, let's call it Sx, X transpose. Now, the autocorrelation matrix would be the same if, that's right, the mean of my sample is 0, or I have 0 normalized, right? I have mean normalized my data, right? But in general, the autocorrelation matrix is different. Okay. Good. Let's see an application of all this. So we'll see a couple of applications. Let me start with, again, let's stick with computer vision, and then we'll turn into signal processing. How about that? Application of this in computer vision, which is part of your first project. What are correlations? What is that correlation matrix really defining? It's defining how correlated each feature in my feature space is with one another, right? Given a set of samples. Now, it's so obvious. I know I keep repeating the same sentence, but it's so important that you understand that correlations are only given with regard to your samples, right? The original space, Rp, doesn't have any correlations. It's just RP, right? But once I start writing or drawing vectors in my RP, I start creating correlations, meaning that if I know the value of one feature, I automatically know the value of another feature, right? Now, if I am trying to represent, say, human faces, as we said here, right? Remember the pixels of human faces? Now, this pixel right here in my cheek and that pixel next to it are highly correlated, wouldn't you say? They almost have the same value. But this pixel here and probably this pixel on my brow are not correlated at all, probably, right? Most likely. Now, the correlations that I'm going to get when I represent human faces are going to be different than the correlations when I try to represent, say, apples. Right? If I take pictures of apples, the correlation of the pixels, and therefore the features in my feature space, are going to be different. Right? Because apples don't look like faces. And if I try to represent images of cars, guess what? The correlations are going to be different. But this is great news for us, isn't it? Because what is machine learning? Well, one of the goals of machine learning is to classify things, elements, or categories, right? Like categories of category. A category could be face, a car, an apple, an orange, and so on. Well, that just gives me a perfect algorithm, doesn't it? I start with a set of samples of faces, set of samples of apples, set of samples of cars, right? For faces, I compute what type of correlation do I get in faces. For cars, what type of correlations cars give me, the pictures of cars, that is, and the pictures of apples. And then when I get the new image, and I don't know what that image represents, I don't know if it's a car, if it's an apple, if it's a face, I just see which correlations fit to that image. That's your very first classifier in machine learning. Simple as that. You just look at the correlations of the pixels. Now, it's a very primitive algorithm. Don't expect it to do amazing things for you, but it's not a bad algorithm. You'll see. You'll implement it in your project. OK? All right. Second application, let's see. In many applications, in signal processing, especially, for example, speech recognition, it is common to represent the data, or the signal, if you will, as a linear combination of some basis signals. Okay? Like basis vectors, basis signals. So let's see how this is usually done. So imagine that we have an observation X. That's what I observe. Like I'm listening in what's sometimes called the cocktail party problem. I'm in a party, drinking a lot of cocktails, and everyone is speaking at the same time, right? So what I get, if I'm a microphone, right? If I get all the information of all these people talking at the same time, that's X. That's what I observe. That's all the information I have. But in reality, there are multiple people, right? The signals, many original signals that are combined, I'm going to assume linearly, right? With a matrix A plus a noise term. Okay? Now again, S here is a vector of signals, S1 through S, let's say, M. X, it's my observation. And obviously, that has to be X1 through n, some other number. And A is my n by m matrix, right? A is an n by m matrix. And n is just some arbitrary vector or function that represents the noise. Now, let's use the autocorrelation matrix to represent this. So to do that, I'm going to write as x, it's equal to, remember, the expected value of x transpose, right? Which is equal to the expected value of, let's see, x is equal to as plus n. So as plus n times as plus n transpose. Okay? So let's factor this out, shall we? So this is going to be the first one with the first one. So this is equal to as transpose A transpose, right? Plus E of as times n transpose plus now n times S transpose A transpose. So n S transpose A transpose plus the last one n transpose. All right. The expected value of A, it's obviously A. That's a mixing matrix, right? It doesn't do anything. So that's A, the expected value of S transpose A transpose, plus A, the expected value of S n transpose, plus the expected value of n S transpose A transpose, plus the expected value of n transpose. Now, I'm going to call this, as we have done before here, remember the autocorrelation matrix? I'm going to call this the autocorrelation matrix of the signals, right? So I'm going to call this S sub S. This I'm going to call, okay, where am I? Here. This I'm going to call S of Sn. This same thing, it's S of Ns. And this one right here, I'm going to call it S of n, right? Now, this is where we can use all the knowledge that we have worked with. This only depends on the signal, right? Yes? This only depends on the noise, yes? But these two terms depend on both the signal and the noise. And what does this compute? The correlation between the noise and the signal. Can we assume that people are not talking in a way that's correlated with the noise? Generally, right? So, all right. Pretty cool. So I can cancel this out, right? What?
Are you assuming that the noise is zero mean?
The noise, well, yeah, but these all things are, yeah. You could assume these things if you want. That's not a big problem. This is something that you can normalize for. We'll get to all these things later on in the course.
It's color.
Yeah, usually we'll see that we usually, as we showed here with the correlation matrix, we normalize and mean normalize the data for specific scaling reasons that are not important right now. Yeah. Right? So we can eliminate this, and all of a sudden, I have a much more tractable problem, right? I have a problem that only has A SS A transpose plus Sn. That's a very tractable problem. It is also common to assume that your noise is Gaussian and maybe even zero mean, as you were mentioning, right? In which case, that can be substituted for a zero mean Gaussian, right? For which there's only one parameter, the mean, that needs to be estimated, right? When you solve the system of equations. That's a really famous equation that is used in many problems in signal processing. Yes?
In terms of like speaking with regards to correlation of noise, wouldn't magnitude be in consideration in there?
The scale?
Yeah, I mean, it's essentially the scalar.
Right. We'll get to that, as I said, later in the course. But usually you mean normalize and norm normalize all your data, so that your data has zero mean and norm 1. Now remember, be very careful. So if we talk about this the first day of class, if you norm normalize, if you mean normalize, that's fine. But if you norm normalize your data, that means that all your vectors all of a sudden have the same length, usually 1, right, or some scalar s. And that means that all your, what you have done, you've mapped your feature space from the real domain, SP, to the spherical domain of SP minus 1, right? And that has terrible consequences. Because to begin with, as we'll see, we want to work with distributions or estimate distributions that are parametric and tractable. But in the surface of a hypersphere, all the distributions are intractable. There's no way for us to ever hope to estimate, in closed form at least, estimate the parameters of those distributions. And the reason for this is because the normalizing constant of the PDF, remember the normalizing constant we discussed when we defined the PDF? It's a constant that you add to the definition of the PDF such that when you compute the volume, right, you integrate that function, the PDF, it's equal to 1, right? That's what normalizes that function, that PDF, to be of volume 1. Well, it turns out that this, in a nonlinear space, which is the surface of a hypersphere, which is nonlinear, is non-computable, right, in closed form. So there's just no hope for you to estimate the parameters of that distribution. So there are very strong consequences of that. All right, any other questions? Yes?
I must be repeating myself, but for that equation to hold, the noise has to be zero mean.
Yes. Yeah, exactly. Any other questions? All right, so our final application that we're going to start at least discussing today is principal components analysis. It's just another application of all this. Okay, so properties of the covariance matrix. It's symmetric, right? We've established this. It's positive semi-definite, right? Which again means nothing else than X transpose sigma X is always positive or 0. Now, the semi-definiteness of that matrix, sigma X, a covariance matrix, comes from the fact that n may be larger or smaller or equal to p, right? So if n is larger than p, it's going to be definite. But if n is smaller than p, it's going to be semi-definite. That's because I don't have enough equations, remember, right? And the number of equations to solve for my p unknowns, right? And therefore, I'm going to have semi-definiteness, because if I have, say, 3 dimensions and 2 equations, right? Any 2 equations or 2 vectors in my 3-dimensional space are going to define a line, right? So it's just no ways I can find vectors for all the possible dimensions of my space, right? Thus, we can compute with the rank of the matrix, which is the same as defining the range of the space. So remember, quick review, the range of a matrix, right, M, is the same as all the elements of the real space where this is defined such that y is equal to mx for some x in, say, Rb, and of course M is a by B matrix, right? The null space, remember, of the matrix is the orthogonal space of the range, right? And I can define it as the axis in Rb for which mx is equal, oops, not different, is equal to 0. Right? Now, remember the matrix computation book that I mentioned? If you have to review these topics, that is the book to have in your shelf and to use as reference for this, right? It is extremely important that you're familiar, or at least you have access to a book like this that allows you to understand all these different concepts that we'll be using, right? For example, I could take, just as another example, I could take the columns of my matrix M, let's say M1 through, what do you say, B, right? M1, M2 through MB, right? And the span of these vectors, right, it's equal to the range space. Very good. All right. So with that quick overview of matrix computation, let's go back to our equation that we had, which is sigma x v equals v lambda. And this is nothing else than the eigenvalue decomposition of sigma x, right? Now here, V, as I said a few times already, is a matrix whose columns are the eigenvectors. And lambda, it's the diagonal matrix of corresponding eigenvalues. Now, if the rank of sigma x if the rank of sigma x, let's call it Q, is smaller than P, then what does this mean? Anyone? That the eigenvalue is what? Okay, some eigenvalues are equal to 0. How many of them? P minus Q are actually equal to 0, right? Very good. Very good. So that, in other words, means that if we start with a feature space of p dimensions, right, we can project all our samples in the space of q dimensions given by the first non-zero eigenvalue eigenvectors, right, v1 through vq, without any loss, right? So it means that I may start with lots and lots of dimensions, but at the end of the day I realize all these dimensions are not necessary. Why am I representing my data in such a large vector space, right? So let's see an example. Imagine, again, I want to represent faces, images of faces, right? And I take pictures with my camera I just bought the other day. Fantastic camera, you should see it. It's 15 million pixels. Well, 50 million pixels means 50 million dimensions. So p is equal to 50 million. Now, let's say I was able to take, I spent 2 weeks taking pictures with that camera of faces, and I managed to take 100,000 pictures of faces. Well, 100,000 means n is equal to 100,000. So therefore, the largest space I can ever hope to represent with 100,000 samples is of how many dimensions? The maximum I can ever hope. What is it? 100,000? Very close. The answer was 100,000, almost. So if I have 2 samples in 3-dimensional space, or in 2-dimensional space, right? How many dimensions can I represent? 1, right? So if I have 100,000, 100,000 minus 1, right? So 99,999, right? That's the largest space I can ever hope to represent. Now, it is possible that some of these vectors, simple vectors that I have, are linearly dependent, right? For example, if I have in 2-dimensional space 3 vectors, but they are collinear vectors, then they still represent a 1-dimensional space, right? Now think about this. If my camera can take pictures that have 15 million pixels, that means that in this 50 million dimensional space, I can represent every single picture of every single thing you can ever take. It could be an image of a white wall. It could be an image of a black wall. It could be an image of a car, of a tiger, of the sky, of the ocean, of faces, of cars. Now, we said faces are going to have pixels that are highly correlated in some areas, right? So that's even going to most likely reduce the dimensionality even further. So more eigenvalues are going to be equal to 0, right? So why do I want to keep representing my data in a feature space of 50 million dimensions if probably at most 10,000 or less, right, actually have eigenvalues that are different than 0? Of course I don't, right? It's a waste of space and time. So that's the very first thing that I can do. I can just eliminate all the dimensions of my space that are irrelevant. Now, what is an eigenvalue decomposition? An eigenvalue decomposition, remember from this equation that we have right there, is nothing else than a rigid transformation, rigid or Euclidean transformation, right? In fact, it's only a rotation, right? The translation is given by subtracting the mean, and then there is only a rotation. Because the basis vectors, the original basis vectors, right? If I had here in my 2-dimensional space, my original basis vectors, let's call it E1 and E2, have been rotated by V1 and V2 the eigenvectors, right? So this is the same as rotating my space. That's a rigid transformation. Okay? So that's all I'm doing. And the eigenvectors that have an associated eigenvalue of equal to 0 don't have or don't carry any additional information for me. So I can eliminate them immediately. But I could also eliminate the eigenvectors that have a very tiny, small eigenvalue, right? And we'll talk about this on Thursday, and that's what's called principal components analysis. All right? I'll see you Thursday.